Theory of Equations, Matrices and Vector Calculus. This is the core course for 4th semester BSc Mathematics under School of Distance Education, Calicut University. Through this video, we intend to give a brief introduction to the various concepts and important theorems in this course. So, let us begin. Module 1, Theory of Equations. We will begin with the definition of a polynomial. A polynomial of degree n is a function defined by f of x is equal to a0x raised to n plus a1x raised to n minus 1 plus dot 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 plus an, where a0 is not equal to 0 and n is a non-negative integer, and each ai's are fixed complex numbers and are called the coefficients of the polynomial f. We say a complex number alpha is a root or a zero of the polynomial f of x if f of alpha equal to 0. Fundamental theorem of algebra states that every polynomial of degree greater than or equal to 1 has at least one root. So the next theorem states that every polynomial of degree n has n roots. Therefore, if we have a polynomial function of degree n, then it will have n roots. One thing to notice here is that for a polynomial of degree n, all the n roots may not be distinct. For example, if we consider the polynomial equation x minus 2 the whole square equal to 0, it's a polynomial of degree 2 and it will have two roots, but it doesn't have two distinct roots. It has repeated roots which are 2, 2. We will learn more about repeated roots as we go further into the course. So the next theorem is an interesting theorem. So the next theorem states that suppose we have a polynomial function f of x and it has a complex root alpha plus I beta. Then the conjugate of the complex root, which is alpha minus I beta, is also a root of the polynomial. So in conclusion, a complex root always occurs as conjugate pairs. Before moving on to the next theorem, let's quickly recollect what a quadratic surd is. So a quadratic surd is a number of the form a plus or minus root b, where a and b are rational numbers and b is a non-square rational number. For example, 2 plus root 5, it's a quadratic surd. So we'll now see the theorem. So the theorem states that for a polynomial equation with rational coefficients, the root which are quadratic surds occur in conjugate pairs. Therefore, like in complex roots, the quadratic surds also occurs as conjugate pairs. Now moving on to the next theorem. So the next theorem provides a relationship between the roots and the coefficients of a polynomial equation. So the theorem states that if p by q, a rational number in its lowest form, is a root of a polynomial a0x raised to n plus a1x raised to n minus 1 dot 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 plus an is equal to 0, where all the coefficients are integers, then p is a divisor of an and q is a divisor of a0. If a root alpha of f of x is equal to 0 is repeated r times, then alpha is called an r multiple root of the polynomial f of x. So for example, consider f of x is equal to x minus 2 the whole raised to 3 into x minus 5 the whole square into x plus 1. So in this particular example, you can see that the root 2 is repeated 3 times, the root 5 is repeated 2 times, and the root minus 1 is repeated 1 time. So 2 is a 3 multiple root, a 5 is a 2 multiple root, and minus 1 is a single root. So now we will see an theorem concerning multiple roots. So if alpha is an r multiple root of f of x is equal to 0, then alpha is is an r minus 1 multiple root of f dash of x equal to 0, where f dash of x is the derivative of f of x. Now we will see some explicit relationship between roots and coefficients of quadratic and cubic polynomials. So if alpha and beta are roots of a quadratic polynomial, that is ax square plus bx plus c equal to 0, then alpha plus beta is equal to minus b by a, and alpha into beta is equal to c by a. Now, if alpha, beta and gamma are roots of a cubic polynomial ax cube plus bx square plus cx plus d equal to 0, then alpha plus beta plus gamma equal to minus b by a, alpha into beta plus beta into gamma plus alpha into gamma is equal to c by a, and alpha into beta into gamma is equal to minus d by a. Are concerning sums of powers of roots of a polynomial equation. So the first theorem states that the sum of the rth power of a root of an equation f of x is equal to 0 is the coefficient of x raised to minus r in the expression of x into f dash of x by f of x in the descending powers of x, where f dash of x denotes the first derivative of the function f of x. Now from this theorem we can derive the next theorem, which is Newton's theorem on the sum of powers of roots. So this theorem states that if alpha 1, alpha 2 dot 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 up to alpha n are the roots of the polynomial equation x raised to n plus b1 x raised to n minus 1 plus b2 x raised to n minus 2 plus dot 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 plus bn equal to 0, then SR, which is the rth sum of powers of root, that is alpha 1 raised to r plus alpha 2 raised to r dot 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 plus alpha n raised to r, then SR plus SR minus 1 P1 plus dot 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 plus S1 into PR minus 1 plus R into PR equal to 0 if R is less than or equal to n, and SR plus SR minus 1 P1 plus SR minus 2 P2 plus dot 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 plus SR minus n into Pn equal to 0 if R is greater than n. Suppose we are given a polynomial f of x is equal to 0. Without knowing the roots of f of x is equal to 0, we can transform the given equation into another equation where the roots are related to f of x is equal to 0 in a particular way. So we will here explore different transformations that are possible. So suppose we are given a polynomial f of x is equal to a0 x raised to n plus a1 x raised to n minus 1 dot 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 plus an, and the roots are alpha 1, alpha 2 up to alpha n. Therefore, we'll see the first transformation that is possible. So for the first transformation is to form an equation whose roots are k times the roots of a given equation. So in order to form an equation whose roots are k times the roots of f of x, that is k alpha 1, k alpha 2, we simply have to multiply the coefficients of x raised to n, x raised to n minus 1 dot 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 x and the constant term by 1 k square, k raised to n minus 1, k raised to n respectively. The next transformation is to form an equation whose roots are the reciprocal of the roots of the given equation. So in order to form such an equation, we simply have to substitute x is equal to 1 by y. Next transformation is to form an equation whose roots are h less than the roots of a given equation. That is, we have to form an equation whose roots are alpha 1 minus h, alpha 2 minus h, dot 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 up to alpha n minus h. Our given polynomial function is f of x, and we can write f of x as products of its factors. That is, f of x is equal to a0 into x minus alpha 1 into x minus alpha 2 dot 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 up to x minus alpha n. Now give the substitution x is equal to y plus h. Then we get f of y plus h equal to a0 into y minus alpha 1 minus h into y minus alpha 2 minus h into dot 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 up to y minus alpha n minus h. So notice that f of y plus h has alpha 1 minus h comma alpha 2 minus h dot 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 up to alpha n minus h as its root. Therefore, to form an equation whose roots are h less than the roots of a given equation, we had to just give the substitution x is equal to y plus h and simplify the equation. Similarly, to form an equation whose roots are h greater than the roots of the given equation, we just have to minimize the roots by minus h. The last transformation is to form an equation in which certain specified term of the given equation is absent. Consider the equation a0 x raised to n plus a1 x raised to n minus 1 plus dot 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 plus an equal to 0. Now suppose we have to remove the second term, that is a1 x raised to n minus 1. So the first step is to diminish the root of the given equation by h. So we have already seen how to diminish the root. So we substitute x is equal to y plus h into the equation. So we get a0 y raised to n plus n into a0 h plus a1 into y raised to n minus 1 plus dot 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 plus an equal to 0. So we have to eliminate the term n a0 h plus a1 into y raised to n minus 1. So in order to do that, what we do is that we put h is equal to minus a1 by n a0. So by substituting h is equal to minus a1 by n a0, the second term get completely eliminated. Therefore, so in order to remove the second term from this equation, we have to diminish the root by h is equal to a1 by n a0. So if we have to eliminate any other term, we have to similarly diminish the root by suitable h. Reciprocal equations. Let f of x is equal to 0 be an equation with roots alpha 1, alpha 2 up to alpha n. If 1 by alpha 1, comma 1 by alpha 2, comma up to 1 by alpha n are also roots of the same equation, then such equations are called reciprocal equation. Suppose a0 x raised to n plus a1 x raised to n minus 1 plus dot 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 up to an equal to 0 be a reciprocal equation with roots alpha 1, alpha 2 up to alpha n. Then 1 by alpha 1, comma 1 by alpha 2 up to 1 by alpha n are also roots of the same equation. This forces the coefficient of the polynomial to satisfy either of the following conditions. First condition is a0 equal to an, comma a1 equal to an minus 1, comma a2 is equal to an minus 2, etc., etc. Such equations that satisfy this condition is called reciprocal equations of first type. Now second condition, a0 is equal to minus an, comma a1 is equal to minus an minus 1, comma a2 is equal to minus an minus 2, etc., etc. Equations satisfying this condition are called reciprocal equation of second type. A reciprocal equation of first type and even in degree is called standard reciprocal equation. We already know methods to solve quadratic equations. Now we'll study a method to solve standard cubic equations. It's called Cardano's method. So the method has two steps. So the first step is depressing the cubic polynomial. So suppose we are given a standard cubic polynomial a x raised to 3 plus b x square plus c x plus d equal to 0. So we apply the substitution x is equal to y minus b by 3a. to the cubic equation. So after substitution, we get a into y raised to 3 plus c minus b square by 3a into y plus d plus 2b cube by 27a square minus 3bc by 3a equal to 0. So we see that the y square term is missing. So this step is called depressing the cubic polynomial. So our depressed polynomial is of the form y cube plus ay equal to b. So the second step is solving for the depressed cubic polynomial. To solve the depressed cubic polynomial, we first find s and t such that 3st equal to a and s cube minus t cube is equal to b. So after finding such s and t, we'll get that y is equal to s minus t. So we can solve for y, and after solving for y, we can easily solve for x, thus solving the cubic polynomial. We have seen methods to solve cubic polynomials now. Similarly, there exists a method called Ferrari's method to solve quartic equations. So we have formulas which gives roots of linear, quadratic, cubic and quartic equations. However, there exists no formula to solve general quintic or higher order equations. And this theorem was proved by the famous mathematician Abel. We go through some rules which helps in understanding the nature of the roots of a polynomial by looking at the signs of the coefficients and the powers of x. So the first rule is that if the coefficient of a polynomial equation are all positive, then the equation has no positive roots. The second rule is that if the coefficient of the even powers of x are all of one sign and the coefficient of odd powers of x are all of the opposite sign, then the equation has no negative roots. Third rule is that if the equation contains only even powers of x and the coefficient are all of same sign, then the equation has no real roots. We have the rule of signs, which states that in any polynomial equation f of x is equal to 0, the number of real positive roots cannot exceed the number of changes in the signs of the coefficient of the terms in f of x, and the number of real negative roots cannot exceed the number of changes in signs of the coefficient of f of minus x. Module 2, rank of a matrix. Let A be a m cross n matrix. Then if we retain any t rows and t columns of A and deleting the rest, then we obtain a t cross t square submatrix of A. The determinant of this square submatrix of order t is called a minor of A of order t. Now we will define rank of a matrix. The number R is called rank of a matrix if it satisfies the following properties. First property, there is at least one non-zero minor of order R. Second property, every minor of order R plus 1 is 0. So if the number R satisfies both these properties, it is called rank of a matrix A. Now we'll look upon some remarks. First one is the rank of a matrix A is the largest order of a non-zero minor of rank A. Second one, the rank of a matrix A is denoted by row of A. Third one, the rank of any non-singular matrix of order n is n. Fourth one, the rank of any non-zero matrix is greater than or equal to 1. And fifth one, the rank of a zero matrix is taken as 0. Elementary transformation of matrices. An elementary transformation is an operation of any one of the following types. First, the interchange of any two rows or columns. Second, the multiplication of elements of any row or column by an non-zero number. Third, the addition to the elements of any row or column, the corresponding elements of any other row or column multiplied by any other number. Next, equivalent matrices. So we say two matrices are equivalent if one can be obtained from another by a finite number of elementary transformations. We can use elementary transformations to determine the rank of a matrix, and the two theorems stated below shows us how. So the first theorem states that every m cross n matrix using a sequence of elementary transformation can be reduced to any one of these four forms, where IR is the identity matrix of order R and each zeros are zero matrices of appropriate order. Now, the second theorem states that if an m cross n matrix A can be reduced to any one of these forms by a sequence of elementary transformation, then the rank of A is R. So, combining these two theorems, we can see how elementary transformations can be used to determine the rank of a matrix. Now, we will use elementary transformation to determine the inverse of a matrix. Suppose we have to find the inverse of matrix A. So first step is to write A is equal to IA, where I is the identity matrix. Now the second step is to perform a suitable set of elementary row transformation on matrix A on the left and the prefactor I of A on the right till we reach the result I is equal to BA. Then B is the inverse of the matrix A, which is the result we needed. Is a simpler form that we can reduce an matrix into, and it is really helpful in finding the rank of a matrix. A matrix is in echelon form when it satisfies the following three conditions. First, each row containing a non-zero number has the number 1 appearing in the row's first non-zero column, and this term is called as the leading one. Second condition, the column numbers of the columns containing the first non-zero entries in each of the rows strictly increase from the first row to the last. The third condition, any row which contains all zeros is below the row which contains a non-zero entry. And also we have a reduced echelon form, and a matrix is in reduced echelon form when, in addition to all these three conditions, all the entries above the leading ones are zero. This is an example showcasing the row echelon form and the reduced row echelon form of matrix A. So we are given a matrix A, and below that we have the row echelon form of matrix A, and below that we have the reduced echelon form of matrix A. Module 3, System of Linear Equations. System of linear equations. A system of linear equation is a finite collection of linear equations in same variables. So here we are given a system of linear equations. So a solution of a linear equation is an n-tuple s1 s2 dot 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 sn of numbers that makes each equation a true statement when the values s1 s2 up to sn are substituted for x1 x2 up to xn respectively. The set of all solutions of a linear equation is called the solution set of the system. So any system of linear equation can have the following exclusive conclusion. First one, it can it won't have any solutions. Second one, it will have a unique solution. And third one, it will have infinitely many solutions. So, and we say a linear system is consistent if it has at least one solution, and it is said to be inconsistent if it does not have any solution at all. We can represent the above mentioned system of linear equations in the matrix form Ax equal to B, where the matrix A is the set of all coefficients and B is the column matrix containing the constants and X is the solution matrix. Now we'll introduce the augmented matrix. So the augmented matrix AB is obtained by placing the constant column matrix B to the right of the matrix A. So in the above system of linear equation Ax is equal to B, the augmented matrix AB will be something like this. Let us now move on to the important part of solving system of non-homogeneous equation. So how do we solve a system of non-homogeneous equation? Step 1. Write down the corresponding matrix equation Ax equal to B. Step 2. Using elementary row transformation to obtain the row echelon form of the augmented matrix AB. Step 3. Checking if the rank of A equal to the rank of the augmented matrix AB. Now depending upon this, we have two cases. Case 1. If rank of A is not equal to rank of augmented matrix AB, then the system is inconsistent and has no solution. Case 2. If rank of A equal to rank of augmented matrix AB, then the system is consistent. Now case 2 has two further cases. Case 2a, if rank of A equal to rank of augmented matrix AB is equal to the number of unknowns, then the system has a unique solution. Case 2b, if rank of A equal to the rank of augmented matrix AB is less than the number of unknowns, then the system has infinitely many solutions. Let us now introduce the notion of eigenvalues and eigenvectors of a matrix. A non-zero vector x is called an eigenvector of a square matrix A if there exists an scalar lambda such that A acting upon x gives lambda times x. Then we call lambda the eigenvalue or the characteristic value of A. Now let x be an eigenvector of matrix A. Then there must exist an eigenvalue lambda such that A acting upon x gives lambda times x, or equivalently Ax minus lambda x equal to 0. Now since x, the eigenvector x is a non-zero vector, we get determinant of A minus lambda I, where I is an identity matrix, equal to 0. Now this equation is called the characteristic equation of A, and its roots determine the eigenvalues of A. Some remarks on eigenvalues and eigenvectors. First one, the eigenvalues of a diagonal matrix are same as its diagonal elements. Second one, the eigenvalues of a triangular matrix are also same as its diagonal elements. Third one, a matrix A and its transpose has the same characteristic values. Fourth one, if A and P are square matrices of same order and P is invertible, then the matrices A and P inverse AP have the same characteristic values. Fifth one, two similar matrices have the same characteristic roots. So two matrices A and B are said to be similar if there exists some invertible matrix P such that B is equal to P inverse AP. Now we'll look into some special matrices. First one, Hermitian matrix. A matrix A is said to be Hermitian if conjugate transpose of A is equal to A itself. Second, skew Hermitian matrix. A matrix A is said to be skew Hermitian if conjugate transpose of A is equal to minus A. Third, unitary matrix. A matrix A is said to be unitary if conjugate transpose of A is equal to A inverse. Cayley-Hamilton theorem is an important theorem regarding the characteristic equation of a matrix. So the Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. So we know that for every square matrix A, we have a corresponding characteristic equation. And this theorem states that the matrix will satisfy its characteristics equation. Module 4, Lines and Planes in Space. Vector is a quantity that has both a magnitude and a direction. For example, force. Force has a magnitude and also a direction. And another example is velocity, which has both a direction and a magnitude. So we will usually denote vectors by lowercase alphabets such as a, b, p, etc. Now coming to scalars, scalar is a quantity that only has a magnitude. For example, length, because it only has a magnitude and it doesn't have any direction. Another example is area. Now for a vector, we will have an initial point and a terminal point, and the length of the vector will be the distance between the initial point and the terminal point. So for a vector A, the length will denote by modulus of A. So the length of the vector is also called norm of the vector. And if a vector has only length 1, then it's called a unit vector. And we say two vectors A and B are equal if they have the same length and the same direction. For a vector A equal to a1, a2, a3, the norm or the length of the vector modulus A will be square root of a1 square plus a2 square plus a3 square. Now that we have defined what a vector is, let us see some operations on vectors. So first is vector addition. Given two vectors a and b, how do we define the operation a plus b? So suppose we have vectors a given as a1, a2, a3 and vector b where it is given as b1, b2, b3. So a plus b is defined as the vector a1 plus b1, a2 plus b2, a3 plus b3. So basically we add the corresponding components. Okay, now that we have defined vector addition, we'll see some basic properties of vector addition. So first property is that vector addition is commutative. A plus b is equal to b plus a. Okay. Second property is it's associative. U plus v plus w equal to u plus v plus w. Okay. Third property is a plus 0 vector equal to a. So if we add a with any with a 0 vector, it gives back you the vector. Okay, 0 vector is basically where all the components are 0. Okay, d a plus minus a equal to 0. So geometry speaking, minus a will denote the vector having the length same as vector a, but the direction will be opposite to that of a. The next operation is scalar multiple. For a scalar c and a vector a, the scalar multiplication c into a is obtained by multiplying each component of a by c. That is ca equal to the vector c into a1, c into a2, c into a3. Okay. Geometrically speaking, if vector a is not equal to 0 and c is greater than 0, then the vector ca has the same direction as that of a, And if C is less than 0, then the vector CA has opposite direction that of A. Okay. And now regarding the length of CA. So the modulus of CA equal to modulus of C into modulus of A. Okay. Now we'll see some basic properties of scalar multiplication. First is C into A plus B is equal to CA plus CB. Second condition, C plus K into A is equal to CA plus KA, where C and K are scalars. Third condition, C into KA is equal to CK into A, where C and K are scalars. And fourth condition, 1 into A will give you A itself. The next operation on vectors is inner product. The inner product or dot product of two vectors A and B, denoted as A dot B, is defined as modulus of A into modulus of B into cos gamma, where gamma is the angle between the vector A and B. So we can also define inner product in terms of components. So if A is equal to A1 comma A2 comma A3 and vector B equal to B1 comma B2 comma B3, then A dot B equal to A1 B1 plus A2 B2 plus A3 B3. So it's basically component wise multiplication. Okay, we say two vectors A and B are orthogonal if A dot B equal to 0. Using the formula for the dot product, we can find a formula for the angle between two vectors A and B. So if gamma is the angle between two vectors A and B, then cos gamma is equal to A dot B by mod A mod B. Now next, if we want to find the component of a vector A along the direction of another vector B, then we can find that component using the formula P is equal to mod A into cos gamma, where gamma is the angle between A and B. The next operation on vector is the cross product. The vector product or cross product A cross B of two vectors A is equal to A1, A2, A3 and B is equal to B1, B2, B3 is a vector V which can be found in terms of determinant of the matrix I, J, K, A1, A2, A3 and B1, B2, B3, where I, J, K are the unit vectors along the direction of the axis X, Y and Z. And an important thing to notice is that when you cross two vectors A cross B, we always get another vector V, unlike in the case of dot product, where when you dot two vectors A and B, you always get a scalar. And few other properties of a cross product is that if A and B are in the same direction, then the cross product V is equal to 0. And if A and B are in the opposite direction, then also the cross product V is equal to 0. Also, there's a formula for finding out the modulus of the cross product V. So mod V is equal to mod A into mod B into sine gamma, where gamma is the angle between the vectors A and B. Also, another important thing to note about cross product is that the cross product of vector A and B, V, is always mutually perpendicular to A and B. So let us now look through the properties of cross product. First property, for any scalar L, LA cross B is equal to L into A cross B equal to A into LB. Second property, the cross product is distributive with respect to vector addition. That is, A cross B plus C equal to A cross B plus A cross C. Third property, vector product is not commutative, rather it's anti-commutative. That is, B cross A equal to minus of A cross B. Third property, in general, cross product is not associative. That is, A cross B cross C is not equal to A cross B cross C. The next operation is scalar triple product. The scalar triple product of three vectors A, B and C is defined as A dot B cross C. So in order to find the triple product, just have to find the determinant of the matrix A1, A2, A3 and B1, B2, B3 and C1, C2, C3, and the determinant of this matrix will give the scalar triple product of A, B and C. Now we have two theorems. The first theorem states that three vectors are linearly independent if and only if their scalar triple product is non-zero. So if we are given three vectors A, B and C, to check if they are linearly independent, we have to just find out their scalar triple product. If it is not equal to 0, they are linearly independent. If it is equal to 0, they are not linearly independent. And the next theorem states that the scalar triple product of three coplanar vectors is 0. So coplanar vectors means they all lie in the same plane. So the theorem states the scalar triple product of three coplanar vectors is 0. Let us now see how to represent lines and planes in space as equations. So first is equation of a line in a space. So suppose L be a line in space which passes through the point P0, which is denoted by the coordinates x0, y0 and z0, and is parallel to the vector v is equal to ai plus bj plus ck. Now for any point P denoted by the coordinates x, y, z on L, the vector P0P is parallel to V. That is, the point P lies on L if and only if the vector P0P is a scalar multiple of V. So this gives the equation of a line. So the equation of the line will be x is equal to x0 plus TA, y is equal to y0 plus tb, and z is equal to z0 plus tc. We will now derive a formula for distance of a point to a line in space. Suppose we have to find the distance of point S to the line that passes through point P and is parallel to vector V. The distance between the point S and the line will be the length of the component of vector PS normal to the line. That is modulus of ps sine theta, where theta is the angle between the vector ps and vector v, or equivalently we can write it as vector ps modulus of vector ps cos vector v by modulus of v. Therefore the distance from a point S to a line through P parallel to vector v is given by d is equal to modulus of vector ps cross vector v by modulus of v. Equation of a plane in space. Suppose M is a plane that passes through the point P0 denoted by x0, y0 and z0 and is normal to the non-zero vector n is equal to ai plus bj plus ck. Then for any point P denoted by x, y, z on M, the vector P0P is orthogonal to n. That is, n dot vector P0P equal to 0. Now substituting for vector n and vector P0P and simplifying the equation, we get that a into x minus x0 plus b into y minus y0 plus c into z minus z0 equal to 0, which is the required equation. A cylinder is a surface generated by a line which is always parallel to a fixed line and passes through a given curve. The fixed line is called the axis of the cylinder, and the curve is called the guiding curve or the generating curve. If the guiding curve is a cylinder, then we get our usual cylinder, which is called a right circular cylinder. And since a cylinder is generated by straight lines, it extends to infinity on both its sides. And the degree of the equation of the cylinder depends upon the degree of the equation of the guiding curve. A cylinder whose equation is of second degree is called a quadratic cylinder. A quadratic surface. Quadratic surface is the graph in space of a second degree equation in x, y, and z. The most general form of a quadratic surface is ax square plus by square plus c z square plus dxy plus eyz plus fxz plus gx plus hy plus jz plus k equal to 0, where a, b, c, d, e, f, g, h, j, k are all constants. So examples of quadratic surface are, first one, ellipsoid, which is represented by the equation x square by a square plus y square by b square plus z square by c square equal to 1. Second example is a cone, which is represented by the equation x square by a square plus y square by b square equal to z square by c square. All of us are familiar with the Cartesian coordinate system or the rectangular coordinate system, where each point P is represented by the ordered tuple x, y, and z. Here we will study some new coordinate system. The first one is cylindrical coordinate system. So in cylindrical coordinate system, every point P is represented by the ordered tuple r, theta, and z, where r and theta are polar coordinates for the vertical projection of P on the xy plane, and z is the rectangular vertical coordinate. Now we can find equation relating the Cartesian coordinate system and the cylindrical coordinate systems. So these equations are x is equal to r cos theta, y is equal to r sin theta, z is equal to z, and r square is equal to x square plus y square, and tan theta is equal to y by x. Spherical coordinate system. In spherical coordinate system, every point P is represented by the ordered tuple rho, theta, and phi, where rho is the distance from the origin to the point P. So rho is always greater than or equal to 0. And theta has the same meaning as in the polar and the cylindrical coordinates, and theta has no restrictions. And phi is the angle between the positive x-axis and the line from the origin to the point P. And we restrict phi between 0 and pi. For the equations relating spherical coordinate system and the Cartesian coordinate system, the equations are x is equal to rho sine phi cos theta, y is equal to rho sine phi sin theta, z is equal to rho cos phi, and rho square is equal to x square plus y square plus z square. Consider the function r of t is equal to x of t I plus y of t j plus z of t k. Now notice that as the scalar variable t changes, the points x of t, y of t, and z of t traces out some geometric object in space. And such geometric object is called space curve or arc. So simply saying, a space curve is the locus of the point x, y, and z whose coordinates are functions of a single variable t. Now let us define what a vector function or vector valued function is. So a vector function or a vector valued function on a domain set D is a rule that assigns a vector in space to each element in D. So the interval D, it's usually real numbers, and sometimes it can also be regions in the plane or space. Now that we have defined what a vector valued function is, let us introduce the concept of limits, continuity, and differentiability in the context of vector valued function. Let's start with the concept of limit. We define limits for vector valued function similar to the way we define limits for real valued function. Let r of t is equal to f of ti plus g of tj plus h of tk be a vector valued function and L be a vector. We say that R has a limit L as t approaches t0 and denote it by limit t tends to t0 R of t is equal to L. The problem given below and the solution will give more clarity on how to find the limit of vector valued function. So the limits are calculated component wise, similar to how we do for real valued function. Continuity of a vector valued function is also defined similar to that of a real valued function. A vector valued function r of t is continuous at a point t is equal to t0 in its domain if limit t tends to t0 r of t minus r of t0 equal to 0. A function is said to be continuous if it is continuous at every point of its domain. Then we have the component test for continuity at a point. So the component test for continuity at a point states that a vector valued function r of t is equal to f of ti plus g of tj plus h of tk is continuous at t is equal to t0 if and only if the component functions f, g and h are continuous at t0. A vector valued function r of t is equal to f of ti plus g of tj plus h of tk is differentiable at a point t0 if the component function f, g and h are differentiable at that point. And a vector valued function r is said to be differentiable if it is differentiable at every point of its domain. The differentiating rules for a vector valued function is same as the rules for differentiating scalar functions. Constant vectors. A constant vector is a vector that doesn't change its magnitude or its direction. Now we have a theorem related to constant vectors. So the theorem states that the necessary and sufficient condition for a vector function f of t to be constant is that df by dt equal to 0, that is the constant vector. Integral of vector valued function. The infinite integral of a vector valued function r with respect to t is the set of all antiderivatives of r, denoted by integral of r dt. So if capital R is any antiderivative of small r, then integral of r of t dt equal to capital R of t plus c. Now for definite integral, if the components of the vector valued function r of t are integrable over the period a comma b, then so is the vector valued function r of t